Nuclear reactions. This video covers nuclear energy generation. What is nuclear fission? What is nuclear fusion? We'll start with nuclear fission. Nuclear fission is splitting a nucleus. It produces large amount of energy that can be harvested for energy consumption. That's to light our homes, power our smartphones. Fission means to divide, and that's exactly what is happening. The nucleus is divided. During fission, very large nuclei, such as uranium and plutonium atoms, are bombarded with neutrons. That means hit with neutrons. Recall that atoms are made up of three parts: electrons, protons, and neutrons. The neutrons are the part that we're talking about here. You throw it at a very large atom, and it produces an isotope. That's an atom with extra or missing neutrons. In this case, we gave it extra neutron, so the isotope has extra neutrons. The resultant isotope is too unstable and decays quickly, dividing into smaller nuclei and free neutrons. Free neutrons means neutrons that are not bound to a nucleus yet. It's a quick process. They're soon going to be bound with the nucleus, but in the meanwhile, it's a free neutron. Recall that the reason nuclei decay is when the strong force binding protons and neutrons together is overcome by the electromagnetic force trying to separate the positively charged protons. Though the strong force is very strong and operates on both protons and neutrons, it only binds protons and neutrons that are in close proximity to each other. That is, it only works on protons and neutrons that are close enough to touch. Fighting the strong force is the electromagnetic force trying to separate like charges. In this case, the like charges are the positively charged protons. Just like siblings that are too much alike and tend to fight when they should be getting along with each other, the protons are too much alike and tend to fight unless given enough space. The electromagnetic force, often called the electric force, is acting on the protons to split apart the nucleus. The strong force, on the other hand, is trying to keep the nucleus together. Adding that extra neutron is the straw that broke the camel's back and causes the nucleus to split into smaller nuclei. The smaller nuclei are more stable than the original large uranium isotope and do not need to decay further. Their strong force is more powerful than the electrostatic repulsive force of the protons repelling each other. The strong nuclear force, then, keeps the nucleus together. During fission, a small amount of mass gets converted into a tremendous amount of energy. The free neutrons, meaning those that are not attached to protons yet, from the previous decay can be used to bombard other uranium nuclei that might be nearby, keeping the reaction going. You might have heard of this guy called Albert Einstein. Yes? No? While not the first to notice a relationship between mass and energy, Albert Einstein was the first one who proposed that mass and energy are directly related in his special theory of relativity. I'm simplifying his theory quite a bit here, but roughly, the theory presents that mass can be converted to energy and energy can be converted to mass, that they're related, they're part of the same entity. The relationship between the two is given by the famous equation E equals mc squared, where c is the speed of light. The speed of light, for those of us who don't have this number memorized yet, is about 300 million meters per second, which is about 700 million miles per hour. Okay, that is fast, which means that it only takes a tiny bit of mass to get a huge amount of energy. 1 gram of mass can be converted to 100 trillion joules of energy. That's 1 times 10 to the 14th. That's huge, but really, do you know what joules are? That's about what one U.S. citizen uses each year. To give you a frame of reference on how much energy that is from 1 gram, consider how many gallons of gasoline it takes you to get to and from school each week. Okay? Every gallon's about 4,000 grams. Wow. If we could extract the energy in 1 gallon of gasoline directly rather than burning it, we would have enough fuel for you to use for 4,000 years. We're not there yet, though. The neutrons given off can be used to fuel further reactions, like dominoes knocking into each other. This sequence of one reaction giving off neutrons that are used to fuel another reaction is called a chain reaction. Reactions are tightly controlled in power plants by adding materials that absorb the excess neutrons before they can fuel a second reaction. Here's a diagram of a nuclear reactor. It's actually two nuclear reactors. The place where the nuclear fuel is decayed and the heat is captured. The orange is showing the fuel surrounded by control rods. So these green things are control rods. And this is the fuel. That orange, burning orange, is fuel. When lowered, the rods absorb neutrons. These rods control the number of neutrons that are free to bounce around and start a nuclear decay reaction. The neutrons get absorbed by the rods when they are lowered instead of going on and hitting an isotope, causing it to decay. So this neutron bounces into there and gets absorbed. Instead, the neutron is absorbed by the material in the rod without causing a decay. This stops the neutron from achieving critical mass, which is the decay chain reaction. However, when raised, the neutrons are free to bounce into other isotopes. So this one shows it raised. And this neutron can then go bounce over there. Neutron over here could go bounce over here, and the reaction gets hotter and hotter. You get more and more chain reaction going on, causing nuclear decay, which causes more neutrons to form, which bounces into other isotopes, causing nuclear decay, which causes even more neutrons to form. Ah, what a cycle. Notice how new uranium atoms are needed to continue the reaction. The neutrons do not cause krypton and barium to decay further. If there are no uranium atoms, then no further reaction can occur. Only the uranium in the fuel rod decays when hit with neutrons. Also notice how more and more neutrons are available from each reaction. So you have one neutron hitting a uranium isotope produces two smaller isotopes, but it also produces two neutrons. 1, 2. So you had one coming in and you're producing two. So you have even more from the chain reaction. Just as dominoes need that initial push to begin the reaction, so too does nuclear fission. An initial push is needed to begin a chain reaction. After the initial push, more material is needed to sustain it. The amount of material, that's the uranium, required to sustain a nuclear chain reaction at a constant rate is called its critical mass. Too little and no further reaction is generated. No fuel, no reaction. Too much and you have one big bang. The energy given off by the fission is used to boil water. The boiling water is used to turn the turbines generating electricity. This is the same process used gas and coal burning power plants. It burns fuel that heats water, and then that water is used for the turbine. It's not directly converting burning coal into electricity. It goes burning coal, water, electricity. Nuclear, boiling water, electricity. Which means the water cooling towers associated with nuclear power plants are for cooling the water used in the turbines, not for controlling the nuclear reactions. This picture is actually from a coal-fired power plant in Germany. It's not from a nuclear plant. Now let's talk about nuclear fusion. The sun uses a different nuclear energy generation from fission called fusion. Fusion combines two smaller nuclei into one bigger nucleus. Another way to say it is fusion fuses atomic nuclei together. Fuses means coming together. So fusion fuses atomic nuclei together. Recall fission splits it apart? Well, this one brings them together. Fusion occurs when multiple, generally hydrogen but not always, multiple isotopes come together at incredibly high speeds, speeds only found when the temperature is millions of degrees Celsius. These extremely high temperatures are found in the center of stars, including our Sun. Most stars are composed mainly of hydrogen, with heavier elements formed in the center due to this fusion. Ever wonder where gold and uranium originally come from? Fusion inside stars. When these stars go supernova, their elements are then spread out throughout the universe for some unsuspecting planet to form. Now you know where gold and silver is formed. I hope that you enjoyed this mini lesson on fusion, which is fusing together the sun, and fission, which is splitting apart from. Enjoy.